Welcome to this walkthrough of problem number 1262, greatest sum divisible by 3. In this session, we'll explore how to solve this intriguing problem efficiently, breaking down the intuition, approaches, and optimizations step by step. Let's get started. In this problem, we are tasked with finding the maximum possible sum of elements from a given integer array, such that the resulting sum is divisible by 3. The array, nums, contains non-negative integers, and we are guaranteed that it has at least one element. For the input format, we are given an array nums where the length can range from 1 to 10,000, and each element in the array falls between 0 and 10,000. The output will be a single integer representing the maximum sum of the array's elements that meets the divisibility condition. Let's explore this through some examples. In the first example, the input array is 3, 6, 5, 1, 8. The sum of all elements in this array is 3 plus 6 plus 5 plus 1 plus 8 equals 23. However, 23 is not divisible by 3. To achieve a sum divisible by 3, we can remove the element 5, resulting in the sum 3 plus 6 plus 1 plus 8 equals 18. Since 18 is divisible by 3, it is the maximum valid sum that can be obtained from this array. Now, consider the second example, where the input is 4. The only element, 4, is not divisible by 3, and there are no other elements to adjust the sum. Therefore, the output in this case is 0. In the third example, the input array is 1, 2, 3, 4, 4. The sum of all elements is 1 plus 2 plus 3 plus 4 equals 14, which is not divisible by 3. To make the sum divisible by 3, we remove the smallest element that brings the sum to a multiple of 3. In this case, removing 1 results in a new sum of 14, 1 equals 12, which is divisible by 3. Thus, the maximum sum divisible by 3 that can be achieved is 12. This example illustrates how careful selection of elements to exclude is crucial in solving this problem efficiently. Now, let's consider some constraints and edge cases. The constraints specify that the array length can go up to 10,000, and each element can be as large as 10,000. This means our solution must be efficient and handle large inputs gracefully. For edge cases, if all elements in the array are already divisible by 3, the output will simply be the sum of the entire array. On the other hand, if the array contains only one element that is not divisible by 3, the output will be 0. Additionally, when sums are very close to being divisible by 3, it's important to carefully choose which elements to remove in order to maximize the result. These considerations will guide us as we develop an optimal solution. To tackle the problem of finding the greatest sum divisible by 3, let's first consider the brute force approach. The intuition here is straightforward: examine all possible subsets of the array, calculate their sums, and check if each sum is divisible by 3. Among these, we keep track of the maximum sum that meets the condition. The steps involve generating all subsets, computing their sums, and verifying divisibility. However, this method is extremely inefficient as generating all subsets requires O(2 to the power of n) time, and with additional O(n) work for checking sums, the overall complexity becomes O(n*2 to the power of n). This makes it impractical for large inputs, especially in competitive programming, where efficiency is crucial. The trade-off here is simplicity versus scalability, as the exponential complexity quickly renders it infeasible for larger arrays. Now, to overcome the inefficiency of the brute force method, we can use a dynamic programming approach. The key insight here is that we don't need to explicitly examine all subsets. Instead, we can track 3 states representing the maximum sums that leave remainders of 0, 1, and 2 when divided by 3. This is based on the observation that adding any number to a current sum only affects these remainders in specific ways. By iteratively updating these states, we can ensure all possibilities are considered without generating subsets. The process starts with initializing an array, dp equals 0, inf, where each index corresponds to a remainder. For each number in the input, we update this array to reflect how the number impacts the maximum sums for each remainder. At the end of the iteration, the value at dp, 0, gives the maximum sum divisible by 3. This approach is much more efficient, with a time complexity of O(n) and constant space, but it does require familiarity with modular arithmetic and state updates. The dynamic programming approach was chosen due to its efficiency and scalability. Compared to the brute force method, which becomes infeasible for larger inputs, the DP approach's linear time complexity makes it well suited for this problem. It elegantly leverages modular arithmetic and state tracking to deliver an optimal solution without significant computational overhead. The real breakthrough here is the realization that we only need to track 3 states, remainders of 0, 1, and 2, rather than examining all subsets explicitly. This dramatically reduces complexity while ensuring correctness. However, it's worth noting that while this approach is highly efficient, it may be less intuitive for beginners unfamiliar with modular arithmetic or dynamic programming concepts. For very small inputs, the brute force approach might still be sufficient, but the DP solution is preferred for its general applicability and scalability. In conclusion, the dynamic programming approach strikes an ideal balance among efficiency, scalability, and correctness, making it the optimal solution for solving the greatest sum divisible by 3 problem. By focusing on the critical insight of maintaining 3-state variables corresponding to remainders, the approach avoids the inefficiencies of brute force and ensures all possibilities are considered in a structured and efficient manner. To solve this problem, we aim to find the greatest sum of a subset of the array nums that is divisible by 3. At first glance, we might consider a brute force approach. This would involve generating all possible subsets of the array. For an array of size n, there are 2 n possible subsets. This can be achieved by either recursion or by iterating through binary masks, where each bit in the mask indicates whether an element is included in the subset. Once we have the subsets, we calculate their sums and check if they are divisible by 3. If a subset sum meets this condition, we compare it to the maximum sum found so far and update the result if necessary. Finally, after processing all subsets, we return the maximum sum that satisfies the divisibility condition. While this approach is conceptually straightforward, it is computationally expensive due to the exponential growth in the number of subsets with increasing n. To improve upon the brute force approach, we can use dynamic programming, leveraging a key observation about divisibility by 3. Any integer, when divided by 3, can yield a remainder of 0, 1, or 2. Using this insight, we can maintain the maximum subset sums for each remainder category. To achieve this, we define a DP array DP of size 3. Here, DP 0 will store the maximum subset sum divisible by 3, DP 1 will store the maximum subset sum that leaves a remainder of 1, and DP 2 will store the maximum subset sum that leaves a remainder of 2. Initially, we set DP equals 0, INF as the only valid sum at the start is 0, which has a remainder of 0. We then iterate through each number in the array. For each number, we calculate the potential new remainders by adding the number to the current sums in the DP array and updating the array to reflect the maximum possible sums for each remainder. To ensure correctness during the iteration, we use a temporary copy of the DP array when updating the values. This prevents overwriting the current state while processing the elements. Once all numbers have been processed, the maximum sum divisible by 3 will be stored in DP 0, which we return as the result. The key insight here lies in the use of modular arithmetic to categorize and track sums based on their remainders when divided by 3. This approach ensures that all possible cases are considered efficiently, without redundantly examining subsets. Additionally, this dynamic programming solution is highly efficient. Instead of generating all subsets, which takes exponential time, we iterate through the array once and update a constant-sized state array, reducing the time complexity to O(n). The space complexity is also optimized, as the DP array has a fixed size of 3, resulting in O(1) space usage. This compact representation allows us to solve the problem efficiently and elegantly. The dynamic programming approach relies on 2 key data structures, the DP array and a temporary array. The DP array is a fixed-size array of length 3 that tracks the maximum subset sums for remainders 0, 1, and 2. This choice provides a simple and efficient way to store and update state information. During the processing of each number, a temporary copy of the DP array is created to avoid modifying the current state while iterating through the elements. This ensures that updates are performed correctly without introducing inconsistencies. The algorithm itself is implemented in a straightforward way. Starting with an initialized DP array, we iterate through the numbers in the input array, compute the new remainders, and update the maximum sums accordingly. After processing all numbers, the result is simply the value stored in dp, 0. This implementation achieves an optimal balance between clarity, efficiency, and correctness. To see the algorithm in action, let's walk through an example. Consider the input array nums equals 3, 6, 5, 1, 8. Initially, the dp array is set to 0, inf, inf. As we process each number, the dp array updates as follows. For number equals 3, the array becomes 3, inf, inf, since 3 is divisible by 3. For number equals 6, the array updates to 9, inf, inf, because adding 6 to the current sum of 3 gives a new sum divisible by 3. For number equals 5, the array updates to 9, 14, inf, or 14 is the maximum sum with a remainder of 1. For number equals 1, the array becomes 9, 14, 10, introducing a new maximum sum of 10 with a remainder of 2. Finally, for number equals 8, the array updates to 18, 22, 17. At the end, the maximum sum divisible by 3 is stored in dp, 0, which is 18. The time complexity of this process is O(n), as we only iterate through the array once, and the space complexity is O(1), thanks to the fixed-size dp array. When applying this algorithm, it is important to consider edge cases. For an empty array, the result should simply be 0, as there are no elements to form a subset. If the array consists entirely of negative numbers, the algorithm must handle them correctly by initializing dp with negative infinity for non-zero remainders. This ensures that invalid sums are not considered. Finally, if all numbers in the array are non-divisible by 3, the algorithm will return 0, as no subset meets the divisibility condition. These considerations ensure that the solution is robust and handles all possible input scenarios effectively, maintaining correctness across a wide range of cases. The implementation solves the problem using a dynamic programming approach to optimize the solution. The idea is to maintain a dp array where dp, I, represents the maximum sum achievable with a remainder I when divided by 3. This avoids the need to consider all subsets explicitly, which would be computationally expensive. Step-by-step explanation. 1. Initialize the dp array. The array dp is initialized as 0, 0, 0. Each index corresponds to a remainder modulo 3, and initially, the maximum sums for all remainders are set to 0. 2. Iterate through the input array. For each number in the input list nums, we update the dp array based on the current values and the new number. 3. Create a copy of dp. To ensure the current state of dp is not modified while iterating through it, we create a copy named current_dp. This allows us to calculate new values safely. For update the dp array, for each remainder in current_dp, compute the new remainder plus number, %3 if the number is added. Update dp, new_remainder, to be the maximum of its current value or the new sum remainder plus number. 5. Result. The maximum sum divisible by 3 is stored in dp, 0, because sums divisible by 3 have a remainder of 0 when divided by 3. Complexity. Time complexity. The algorithm iterates over the input list and processes a fixed number of states, 3 remainders, making it O(n), where n is the length of nums. Space complexity. The space usage is O(1), since the dp array has a fixed size of 3 regardless of input size. This approach efficiently calculates the result without generating all subsets, making it optimal for large inputs. This is the Java implementation of LeetCode problem number 1262, greatest sum divisible by 3. The solution mirrors the logic of the Python implementation, using a dynamic programming approach to keep track of the maximum sums for each remainder, 0, 1, 2, when divided by 3. Key differences in Java include explicit type declarations, the use of arrays.copy for creating a copy of the dp array, and the math.max function for comparisons. To solve this problem, we start by initializing an array dp with 3 zeros. Each index in dp corresponds to the maximum sum we've calculated so far, where the sum leaves a remainder of 0, 1, or 2 when divided by 3. In the first iteration, we consider the number 3. Since the current dp is 0, 0, 0, we calculate the new sum for each remainder. Adding 3 to the remainder 0 gives us 0 plus 3, %3 equals 0, so we update dp, 0, to the maximum of its current value or 3, which results in dp 0 equals 3. Moving to the next number, 6, we repeat the process. Starting with the updated dp of 3, 0, 0, we add 6 to each remainder. For the remainder 0, 3 plus 6, %3 equals 0, and we update dp 0 to the maximum of its current value or 9, resulting in dp 0 equals 9. The other remainders remain unaffected, so the updated dp becomes 9, 0, 0. Next, we process the number 5. The current dp is 9, 0, 0, and we calculate the new sums for each remainder. Adding 5 to the remainder 0 gives 9 plus 5, %3 equals 2, so we update dp 2 to the maximum of its current value or 14, resulting in dp 2 equals 14. Similarly, adding 5 to the remainder 0 again gives 0 plus 5, %3 equals 2, but since dp 2 is already 14, it remains unchanged. The updated dp becomes 9, 0, 14. Now we consider the number 1. With the current dp of 9, 0, 14, we calculate that adding 1 to the remainder 0 gives 9 plus 1, %3 equals 1, so we update dp 1 to the maximum of its current value or 10, resulting in dp 1 equals 10. Adding 1 to the remainder 0 again gives 0 plus 1, %3 equals 1, but dp 1 remains 10. Finally, adding 1 to the remainder 2 gives 14 plus 1, %3 equals 0, so dp 0 is updated to 15. The updated dp is 15, 10, 14. Now we process the last number in our first example, 8. The current dp is 15, 10, 14. Adding 8 to the remainder 0 gives 15 plus 8, %3 equals 2, so we update dp 2 to the maximum of its current value or 23, resulting in dp 2 equals 23. Adding 8 to the remainder 1 gives 10 plus 8, %3 equals 1, so dp 1 is updated to 18. Lastly, adding 8 to the remainder 2 gives 14 plus 8, %3 equals 0, so dp 0 is updated to 22. The final dp after all iterations is 22, 18, 23. Since we are looking for the greatest sum divisible by 3, we return dp 0, which is 22. In our second example, the input array is 4, 1, 7, 5. We start again by initializing dp equals 0, 0, 0. The first number is 4, and with the current dp of 0, 0, 0, we calculate 0 plus 4, %3 equals 1. This updates dp 1 to the maximum of its current value or 4, resulting in dp 1 equals 4. The updated dp becomes 0, 4, 0. Next, we consider the number 1. With the current dp of 0, 4, 0, adding 1 to the remainder 0 gives 0 plus 1, %3 equals 1, but dp 1 remains 4. Adding 1 to the remainder 1 gives 4 plus 1, %3 equals 2, so dp 2 is updated to 5. The updated dp is now 0, 4, 5. The next number is 7, and the current dp is 0, 4, 5. Adding 7 to the remainder 0 gives 0 plus 7, %3 equals 1, so dp 1 is updated to 7. Adding 7 to the remainder 1 gives 4 plus 7, %3 equals 2, so dp 2 is updated to 11. Adding 7 to the remainder 2 gives 5 plus 7, %3 equals 0, so dp 0 is updated to 12. The updated dp becomes 12, 7, 11. Finally, we process the number 5. With the current dp of 12, 7, 11, adding 5 to the remainder 0 gives 12 plus 5, %3 equals 2, so dp 2 is updated to 17. Adding 5 to the remainder 1 gives 7 plus 5, %3 equals 0, but dp 0 remains 12. Adding 5 to the remainder 2 gives 11 plus 5, %3 equals 1, so dp 1 is updated to 16. The final dp is 12, 16, 17, and the greatest sum divisible by 3 is dp 0 equals 12. Here, we analyze the time complexity of the solution. The process begins with an outer loop that iterates through all elements of the input array nums. If the array has n elements, then this loop will run exactly n times. Now, within each iteration of the outer loop, we have an inner loop that works with the dp array. This DP array always has a fixed size of 3, representing the 3 possible remainders when dividing by 3. Because of this fixed size, the inner loop runs exactly 3 times for each element in nums, regardless of the input size. Inside the inner loop, we perform constant time operations such as calculating the new remainder and updating the DP array. Combining these observations, the outer loop contributes O(n), the inner loop adds O(3) per iteration, and constant time operations remain O(1). When we multiply O(n) by O(3), we get O(3n), which simplifies to O(n), since constants are ignored in big O notation. Therefore, the time complexity of this solution is linear, or O(n). Now, let's examine the space complexity. The DP array, which is the core of this solution, always has a fixed size of 3, regardless of the size of the input array nums. This means it uses O(1) space. Additionally, during each iteration of the outer loop, we create a temporary copy of the DP array called current_DP. Since this copy also has only 3 elements, it requires O(1) space as well. The input array itself does not consume any extra space because we are simply iterating through it rather than duplicating or modifying it. No other data structures are used in this solution, and all computations are performed in place. As a result, the overall space complexity of the solution is O(1), which is constant and independent of the size of the input array. To better understand the efficiency of this approach, let's compare it with a brute force method. A naive solution would involve generating all subsets of the array nums and checking each subset sum to determine if it is divisible by 3. Generating all subsets requires O(2 to the power of n) operations, and checking the sum of each subset could take O(n) in the worst case. This results in a time complexity of O(n*(2 to the power of n), and a space complexity of O(n), which is required for either recursion stack space or storing subsets. In contrast, the optimized dynamic programming solution we are discussing avoids this exponential growth by maintaining only 3 states, corresponding to the remainders 0, 1, and 2, and updating them iteratively. This reduces the time complexity to O(n), and the space complexity to O(1). Additionally, since the algorithm processes each element of the array exactly once and its behavior depends only on the array's length, the time complexity remains O(n) in the best, average, and worst cases, with no variation based on the specific values in the array. Finally, let's solidify our understanding with a mathematical proof of the big O complexity. The outer loop iterates through each of the n elements in the array, contributing O(n) to the total complexity. Within this loop, the inner loop iterates a constant 3 times for every element, performing O(1) operations per iteration. When we multiply O(n) from the outer loop by O(1) from the inner operations, we get a total time complexity of O(n). For space complexity, the key factor is the DP array, which has a fixed size of 3, contributing O(1). No additional data structures are used, and all operations are carried out in place, confirming a space complexity of O(1). In conclusion, this dynamic programming solution is highly efficient compared to brute force methods, achieving linear time complexity and constant space complexity. When solving this problem, there are several common mistakes to watch out for. First, ignoring edge cases can lead to major issues. For example, consider arrays that are empty, consist of just one element, or contain all negative numbers. If these scenarios are not explicitly handled, your code might return incorrect results or, worse, throw runtime errors. Another frequent issue is incorrect subset generation. Forgetting to include all possible combinations, such as empty subsets or subsets of size 1, can result in missed solutions. It's essential to ensure your subset logic is comprehensive and accounts for every possibility. Additionally, brute force approaches can create performance bottlenecks. Calculating the sum of every subset directly, without leveraging optimizations like memoization, can quickly become impractical due to the exponential growth in subsets. Lastly, modulo arithmetic misuse is a subtle but critical mistake. When working with divisibility by 3, failing to handle negative numbers correctly, such as understanding that -3% 3 equals 0, can lead to logical errors. Always validate your modulo operations to ensure accuracy. Misinterpreting the problem statement is another pitfall to avoid. Some might overcomplicate the solution by introducing unnecessary constraints or fail to grasp the core requirement of maximizing the sum divisible by 3. carefully rereading the problem can help ensure a clear understanding of what needs to be optimized. From an interview perspective, there are key insights to keep in mind. Problems involving subsets and divisors often benefit from modular arithmetic and dynamic programming. These techniques allow you to reduce redundant calculations and focus on efficient solutions. For optimization, brute force approaches with exponential complexity are rarely acceptable for large inputs. Instead, be ready to discuss trade-offs and propose efficient methods like greedy algorithms or dynamic programming. Recognizing patterns is another advantage. This problem is part of the subset sum family, where solutions involve exploring combinations of elements to satisfy specific conditions. Identifying this pattern can help you quickly apply known strategies. Finally, discussing edge cases, such as arrays with all negative numbers or containing zeros, shows thoroughness and problem-solving foresight, which interviewers value highly. This problem shares similarities with several related problems, which can provide additional context and practice opportunities. For instance, problem 416, partition equals subset sum, focuses on dividing an array into two subsets with equal sums. This requires careful subset generation and some calculations, much like the current problem. Problem 698, partition to k equals some subsets, takes it a step further by introducing constraints to divide an array into k subsets with equal sums, adding more complexity to the subset logic. Another example is problem 1186, maximum subarray sum with one deletion, which emphasizes maximizing a sum under specific constraints and highlights the importance of dynamic programming for optimization. Lastly, problem 1395, count number of teams, involves choosing subsets with ordering requirements, underlining the need for combination generation and filtering logic. Exploring these problems can deepen your understanding of subset and sum-based challenges. There are also alternative approaches to solving this problem, each with its own trade-offs. A greedy approach involves sorting the array and iteratively building the largest sum divisible by 3. While this can reduce complexity, it may fail in scenarios where smaller elements are necessary to achieve the maximum sum. Another effective method is dynamic programming. By maintaining a DP table that tracks achievable sums modulo 3, you can efficiently find the solution without generating all subsets. This approach has a time complexity of n*k, where k is 3 in this case, making it significantly faster than brute force. Finally, backtracking provides a more systematic way to explore valid subsets. Although still exponential in complexity, it can outperform naive subset generation for smaller inputs by focusing only on subsets that meet the criteria. Each of these approaches has its strengths and weaknesses, so understanding their trade-offs is key to selecting the right one for the context. Thank you for sticking through this session on problem number 1262, greatest sum divisible by 3. We've covered the intuition, approaches, and key takeaways to help you tackle similar problems with confidence. Don't forget to like, share, and subscribe for more tutorials. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!